Howdy, welcome back to my lecture series on astronomy, specifically for my ASTR 103 class, spring of 2022. This is lecture 6, and I'm going to be giving a cursory overview of Newtonian physics. Essentially, I will be covering his 3 laws of motion and the law of gravitation. And then I will be talking about the applications, specifically the astronomical applications of these laws. Now, I would like to preface this discussion by saying that, yes, relativity has replaced Newtonian thought in the sense of providing a different physical underpinnings to why Newton's laws actually apply. Again, specifically in relation to the law of gravity. However, astronomers and physicists still use Newton's methods, or what we refer to as classical mechanics, because relativity only really applies in certain circumstances. I mean, let me back that statement off. It applies on all circumstances, but classical mechanics is frankly simpler to use. And so, in regimes where you're dealing with objects that are fairly slowly moving away from deep gravity wells, it is perfectly adequate to use, as it still provides accurate predictions for the motions of objects. So I just wanted to make that caveat. When I move forward, I'm going to be discussing gravity as a force, even though its current thought is that it actually isn't, but it's simply easier to describe it that way, particularly in the context of classical mechanics or Newtonian physics. All right, disclaimer out of the way. Let's see. Hello. So, this is Isaac Newton. Isaac Newton was born, or lived around, if I remember this correctly, around the 1600s, the late 1600s. He actually was born on the same day that Galileo Galilei died, if you're into that sort of kind of coincidental things. And he was absolutely fundamental. In fact, I would say that he is the father of a branch of physics that has lasted until the early 1900s, and remnants of it still are applicable today. And what he did was, even before Newton came on the scene, physics was still dominated by Aristotelian thought. Heavier objects fall faster than light objects, although Galileo essentially disproved that idea. Aristotle also believed that there needed to be what he referred to as an impetus in order to keep things moving in a straight line. He believed that things naturally came to rest. So Newton's laws were radical at the time. They were formative and, to a certain extent, unexplainable. But again, I will get into that. But one of the most powerful things that Newton's laws were able to do were to replicate the laws of motion that Kepler had arrived at. Kepler had arrived at his laws of motion empirically. He studied the motions of planets, specifically Mars, and he tailored his model to the motion of Mars. And that is what we refer to as an empirical relationship, where it's data-driven. Newton's laws were more fundamental in the sense that they are physically driven, in the sense that it was inductive reasoning. He came up with laws which seemed to predict the outcomes of certain behavior, and then he took those to their natural conclusion, and as it so happened, was able to verify Kepler's laws. And so, in doing so, was able to use his laws to accurately predict the positions of stars, and more so, he provided something of a physical underpinning as to why the planets moved in the ways that Kepler described. So Kepler's motion, or laws of motion, there are three of them. The first one is often referred to as the inertial law. And simply put, it states that in the absence of a net force, an object is either going to be at rest if it was initially at rest, or it's going to continue in a straight line motion if it was initially in that straight line motion. So an object at rest will stay at rest unless acted upon by a net force. An object in motion will stay in motion in the same direction unless operated or influenced by a net force. And what I mean by net force is, or an unbalanced force, is essentially a push or pull in a different direction or speed. And I'll get into force in a moment with Newton's second law. So Newton's first law, the inertial law, seems pretty simple. But again, it refuted or went against Aristotle's law, or Aristotle's notion, because Aristotle believed that all objects naturally want to come at rest, or want to stay at rest. Where Newton's law basically says, no, in the absence of an unbalanced force, an object in motion is going to stay that way for perpetuity, unless it is acted upon by an outside force. What Aristotle failed to realize was that things like air resistance and friction are things. And those are those unbalanced net forces that cause objects to tend to come to rest. I suspect one of the reasons why Aristotle did not really consider this is because he lived in a warmer climate. I think that if he lived in a place where there was ice and he saw the difference between, say, moving on land as opposed to moving on ice, his thinking may have been a little bit different. Then you have Newton's second law of motion, or the force law. Now, this is a fundamental law because it essentially defines what we refer to as the inertial mass. So mass can be defined a few different ways. But the way I like to think of mass is just the amount of matter that is contained in an object. But Newton defined it a little bit more mathematically. He defined it in a moment, which I'll show, but essentially the idea is you have a force, you have some sort of impetus that is applied to an object, and that is, and the acceleration that an object feels, the not just movement, but the constantly increasing movement or the constantly changing of direction of movement is inversely proportional to the mass. So effectively, it is, as most people probably already know, it is far easier to move a smaller mass than it is to move a larger mass. If you were to push on a bicycle, it will be easier to push on a bicycle than to push on a semi-truck. And conversely, most people, if given the only two options, would want to be hit by a bicycle than a semi-truck going at the same speed. And so what we have here is one of the simple, or a very simple equation, and I have found that in nature, nature loves simplicity. Some of the most powerful equations in the universe are simple. E equals mc squared, V equals IR, F equals ma. F equals ma simply says the force applied to an object is equal to the mass of that object times the acceleration of that object. And so in terms of the inertial mass can be defined as force over acceleration. The force needed to move an object divided by the amount that accelerates if that force is applied to it. That tells you the mass of the object. Mass is invariant. It doesn't matter where you are. It doesn't matter what conditions you're in. The mass is going to stay the same depending on most conditions. There are a couple of caveats to that. But in almost all cases with classical mechanics, the mass is not going to change of an object. unless you do something physically to it, like chop it in half or what have you. Another way of writing the equation is A equals F over M, and again, that's more applicable, I suppose, if you want to know the behavior of motion. If you want to know how something is accelerated, then you would write it in this form, where you look at the force that is applied over M. Now, in this slide, I refer to F as the net force. That's a little bit, it's cheating a little bit. Net force really is when you add all of the different forces acting upon a certain object. So my cell phone is, I don't know if you can see it, but my cell phone is sitting here on the desk. My cell phone has a net force of 0, but that is because there are two forces acting on it. There is the force of gravity pushing down, trying to take it to the floor, and there is what we refer to as a normal force of the table pushing up on the phone, keeping it where it's at. And so there are two forces acting upon it, so the net force is the force of gravity plus the normal force equals ma, and in this case A is 0. So when we talk about motion with forces, there are essentially two ways that a force can accelerate something. Now, if you remember from a lecture which I currently have not posted, hopefully by, if you watch this later, lecture 5 will be posted fairly soon. Acceleration is a vector, or what we refer to as a vector. It has a magnitude or a size, and it has a direction. So when you apply a force to an object, to a mass, you can either, or both, change the speed, the magnitude of something of motion, essentially increasing or decreasing the speed of that object, or you can change its direction. The speed can remain the same, but the direction could constantly be changing. And so that's going to be more applicable when we talk about orbits. Particularly, the easiest way to look at it is a circular orbit. The magnitude of the magnitude or the speed of that object remains constant. But because it's constantly moving or constantly changing its direction as it moves, that is an acceleration. And so we know that there must be a force acting upon that object in order to accelerate it around a parent body or a host body. And of course, you can do both. You can change the speed and change the direction of an object when you're doing that. And then we come to Newton's third law of motion, or the reaction law. And ultimately what that states is that for every action there is an equal and opposite reaction. So if you were to push on an object, then if you apply to a force to an object, that object will apply an equal and opposite force to you. This is, again, in astronomy, this is the most applicable example is gravity. The gravitational pull that the Earth exerts on the moon is equal and opposite to the gravitational force that the moon applies to the Earth. Now, later on I'll explain, and hopefully you can, if you look at Newton's second law, you might have an inkling as to why it appears that the moon orbits around the Earth and not the other way around, or something in between. For a more terrestrial example of Newton's third law, walking is a fine example. When you walk, you push down or you push back on the Earth, and then the Earth pushes forward on you. That allows you basically to propel yourself. Now, the reason for why that really works is, again, you're pushing on the Earth with a certain force, and the Earth is pushing on you with a certain force. Obviously, there is a large discrepancy in mass. Because you are far less massive than the Earth, your acceleration is going to be far larger than the acceleration on the Earth. But in a very real sense, you are moving the Earth when you walk. Now, as you know, obviously that force in relation to the mass, in relation to all of the other forces acting on the Earth are negligible, but you are in fact applying a force to the Earth, and trying to affect its rotation. So, you have Newton's third law. As an aside, Newton's third law is what is relevant and really the core of how rockets work. The reason why a rocket works is because it is literally throwing mass out the back end of it in terms of thrust, and then that thrust is applied to the rocket itself, and that allows the rocket to propel forward or up or whatever. So Newton's third law is always true. Again, I use the example of walking, of pushing on the earth pushes on you. Another example is the unfortunate case of a mosquito being hit by a semi-truck. Obviously, the semi-truck has more mass, and so that's why the mosquito goes splat. Although there is a force on the semi-truck itself. More obvious example of this is rocks hitting your windshield. Now, a rock hitting your windshield, the rock is going to fly off or splinter or what have you. But if you were moving fast enough, then that rock the force involved is going to crack your windshield. We come to the force of gravity, and you have the maybe apocryphal story of the apple falling from the tree. And the idea is that Newton was sitting around in his orchard, avoiding the Black Death, and saw an apple fall from the tree, break off from the branch and hit the ground. And he asked the question, why? Why did the apple break off from the tree, and then why did it fall to the ground? And from this, he eventually had the epiphany, or eventually worked out that there must be a force acting upon that mass to break it off and make it fall to the ground. And that had to deal with the mass of the apple and the mass of the earth. And so through his applications of the laws of motion, he realized that this force of gravity, this force of attraction between two masses, or between the apple and the earth, it required the presence of two masses and some distance between them. And he reasoned that the force is proportional to the mass and inversely proportional to the distance in some manner. And through the invention of calculus, which, if you have taken calculus or have to deal with calculus, you can blame Newton for it. Or you can also blame Leibniz, a French mathematician who also concurrently and independently developed calculus from Newton. No, I won't. I was going to go into the differences between Leibniz calculus and Newton's calculus, but I realize that's really not important to you all. So, but anyway, Newton formulated his universal law of gravity, and that force states that there is an attraction between two objects, and that is equal to big G, which is a constant, a numerical constant, or fundamental constant, times the mass of one of the objects times the mass of the second object, divided by the distance between them squared. So if you were to double the mass of one of the objects, you double the force acting upon the force of attraction. Those two objects will be accelerated twice as fast as they were previously. Now, if you were to take those two objects and move them away from each other at twice the distance, then the force of the attraction between those two objects, once you release them, would be 1/4 of the previous force of attraction between them. So it is a steeper function of distance than it is of mass. So as an object gets closer and closer to, or an object falls closer and closer to the Earth, and the force of gravity is that true? I was going to say the force of gravity that applies to it gets larger and larger. G is which is known, again, imaginatively as the gravitational constant. It's a constant. It's one of the six gravitational constants in the universe. There is gravity, there's Coulomb's law, there's Planck's law, or, excuse me, there is the gravitational constant, there's the Coulomb constant, the Planck constant, and a few others. And these are what we call the fundamental constants of the universe. These essentially dictate, these basically six constants dictate everything that we see in the universe. If you were to alter any of these constants even slightly, we would not see the same physics in the universe, and our universe would be drastically different than we see today. And so gravity is what we classically refer to as an inverse square law. As I was saying, the distance, the larger the distance, the steeper the function. Or more specifically, in terms of square, you square the distance, and that is the decrease or increase in force. So if you were to double the distance, the force decreases by a fourth. If you were to triple the distance, the force decreases by a ninth, so forth. And commensurately, if you were to halve the distance, then the force of gravity increases by 4. And if you were to triple the distance closer, then the force of gravity goes by a ninth, and onward and onward. So what are the applications of Newton's laws? What can astronomers use, or what can astronomers do with this set of new laws? And so one of the things that Newton went about looking at was Galileo's experiment, which again was an empirical experiment. Galileo looked at the motions of objects and then deduced from that motion that the acceleration on those objects was the same regardless of the mass of the object. And so Newton came around and said, all right, but Galileo made no claims as to what that force actually, where that acceleration actually derived from. Newton basically said, all right, well, let's look at this. We know that F equals ma. We know that, so we know A, that's the acceleration that an object feels as it's falling. And Newton said, all right, well, I think that the force acting upon that object is gravity. And I have a law which dictates what that force is. So let me set them equal to each other. Let me set ma, the force that we see on the object, equal to the gravitational force that I've derived. And lo and behold, what he found was that the masses of the falling objects disappeared. You can cancel them out numerically. And what you're left with is A, or what we commonly now refer to as G, the acceleration due to gravity, is equal to the gravitational constant times the mass of the Earth, if you're dropping something on the Earth, divided by the radius of the Earth squared. And that gives you approximately 9.8 meters per second squared. Now, you can experimentally do this if you like flying in an aircraft. I've actually seen this done. The difference in height between the bottom of the ground level, sea level, and being in a plane is significant enough that the gravitational acceleration changes slightly. So for people at sea level, gravity is, or G, is around 9.80 meters per second squared. If you're in an aircraft, it's more like 9.8, sorry, flipping that around. If you're on the ground, it's 9.81 meters per second squared. If you're flying in an aircraft, it's 9.80. And if you want to see this for yourself, take a digital scale and a weight of some sort, or a mass of some sort, and weigh it on the basically take a measurement of its weight, and then go up to, and then take it on the flame, and assuming that there is no turbulence, or when there is no turbulence, weigh it again, and what you'll discover is that it weighs less on the Earth, and that's because, or excuse me, it'll weigh less on the aircraft because of the fact that you are further away and the gravity is an inverse square law. It also explains why why astronauts bounce around on the moon. Their acceleration, the acceleration they experience, is g is equal to gravitational constant times the mass of the moon divided by the square of the moon's radius. And as it turns out, if you put those numbers in, the acceleration that you feel on the moon is 1/6 that of the Earth. Hence why they appear like bouncy balls, or they're in a bouncy castle as they're moving around. So if you want to feel like you're losing weight, then go to the moon. You'll feel much better about yourself, I suppose. And so that changes. So the weight of an object, weight and mass, are different concepts. Weight is a force. Mass is the amount of matter that you have. As I stated before, mass is invariant. It doesn't matter where you are. It doesn't. The location is irrelevant. You have the same mass on the Earth. You have the same mass on Jupiter. You have the same mass on Mars, and so forth and so on. Your weight, though, changes. The acceleration that you feel due to gravity changes depending on where you are. As I described, even with the Earth situation, depending on your altitude, you're going to feel a different acceleration. Your weight is going to change. So if you're up high on a mountain, you will have slightly less weight than if you're on the ground. As I said with the moon, if you have less weight. So weight is not invariant. It is location dependent. Which brings us to something referred to as centripetal acceleration. Not to be confused with centrifugal acceleration, which is what we refer to as an emergent force because of changes of frames of reference. But again, I digress. It is centripetal acceleration. I bring up centrifugal acceleration because you may have heard that in your high school physics class. But it's really centripetal acceleration. And centripetal acceleration is what we refer to as a central force. It is a force which is constantly pointed towards the center of revolution, in a way. So for a circle, it's easy to see. It's the center of the circle. The force is perpetually pointed towards the center of the circle. For an ellipse, it is always pointed towards the focus that the mass is located. So when the Earth is revolving around the sun, that is an elliptical orbit, meaning that the Earth is not located, or the sun is not located at the center of that orbit. It's located at one of the foci of that ellipse, and that the force of gravity is pointed always towards the sun, or the centripetal acceleration is always pointed towards the sun. Getting back to circular motion, what this means is, again, what I was referring to just with forces before, is that if you have something in orbit, that is a circular orbit, then its speed, essentially the speed at which it's moving, doesn't change, but its direction does. And because of that, that is an acceleration. Therefore, there must be a force acting on it. If you want a more terrestrial example of this, take a ball on a string and whiz it around your head. In this case, the reason why the ball is sticking around your head is because of the string. There is tension in the string that is holding that ball going around your head. And if you want another example of Newton's first law, let go of the string. And that ball is immediately going to no longer go around in a circle. It's going to go in a straight line path along the velocity vector that it had at that instantaneous point in time. Because the tension is no longer there. There is no unbalanced force in that direction. And so it will fly off in that will fly off straight. Now, obviously, it'll fall because of gravity, but ultimately it will fly out straight in that plane, as it were, in the XY plane. Which brings us to weight and weightlessness. Now, I actually had a first grader recently ask me why there is no weight in why there is no gravity in space, and it took me a moment, and actually the assistance of one of my undergraduates to really make sense of what the first grader was actually asking, because my response was, whoever told you there was no gravity in space kind of told you a porcupine or a fib, because gravity is everywhere. Gravity is technically the weakest of all the forces, but it is the most prevalent of all the forces. You can't escape gravity. There is mass in the universe, so you will always experience gravity somewhere. However, what the child really meant was, why is it that astronauts appear to have no weight when they're in orbit? That weightlessness is sort of a misnomer. They do have weight because there is a force acting upon them, but the appearance of having no force acting upon them is related to centripetal acceleration and what I was talking about before. So, which is related to orbital motion. Ultimately, so let's talk about orbital motion. If you take a really massive cannon and you put a certain amount of gunpowder in it, obviously this is a theoretical cannon, you put a certain amount of gunpowder in it, and you launch a cannonball. That cannonball is going to go through what we refer to as a ballistic trajectory. It's going to be parabolic. It's going to have a certain range, and gravity is going to force it down to the Earth. If you pack that cannon with more gunpowder, that's going to cause the initial velocity of the object to be increased, and so it's going to have a larger range. It will travel fast enough that in the same time period, it will have traveled over a larger distance of travel, or a larger distance, and so obviously its range will be larger. Now, you can take this thought experiment to its natural conclusion, to the point of eventually you can pack this cannon, this theoretical cannon, with enough gunpowder that its range is the same as the circumference of the Earth. And the way I like to think about this is the cannonball is constantly falling, because again, in example A and example B, the cannonball falls down to the Earth. For example C, the cannonball is falling, but manages to always miss the Earth. So there is an acceleration on the cannonball. There's always an acceleration on the cannonball due to gravity. There is A, B, C, and D. And that is obviously the force of gravity. And the reason why we see the ball hit the Earth is because literally the Earth is in the way. If you were to somehow magically shrink the Earth, keep the mass, but shrink the Earth to a much smaller value, then you might actually, in example B, for example, you might actually get an orbit where it misses the Earth. It would be elliptical. There's more to that, but let's still keep with the fact that the Earth actually just gets in the way. If you get a speed high enough, if you have a linear speed high enough, a speed coming out of the cannonball, then you can achieve orbit, and that is described by this. And so the minimum velocity that you need in the forward direction in order to obtain an orbit, which is a circular orbit, is the square root of the constant, the gravitational constant, times the mass of the body you are orbiting around, and the radius of that body. So for the Earth, that would be the mass of the Earth and the radius of the Earth. So that is the first orbit that you could obtain, is a circular one. Now, going back to astronauts and why they appear weightless is the same reason that if you were in the unfortunate incidents of being in an elevator where the elevator cable was cut, you and the elevator both have the same acceleration acting upon you, and so you would in fact feel weightless. You've probably experienced this, something akin to this, in a roller coaster. As you go over a curve or fall down a ramp, your acceleration is closer to the acceleration of the car, and you feel like you're lifting up. That's what gives you that kind of sick in the stomach feeling of kind of just being lifted up off the car. So it gives you that illusion. So that if you take this to its natural conclusion, if you are falling at the same rate, if your acceleration is exact same as the acceleration of your environment, then you will appear weightless in that environment. So the International Space Station is literally falling at with an acceleration of whatever the math turns out to be. It's going to be less than 9.8 meters per second squared. But again, it's the direction of it, which is pointing towards the center of the Earth. And the astronaut inside the ISS is going to be floating is going to be experiencing the exact same acceleration. And so they have the ability to basically float around. That's what gives the appearance of weightlessness. Not that there is no gravity there, just the fact that they are moving at the same acceleration. Now, here, case D, if you were to, again, even continue this thought experiment, hopefully I didn't say to its natural conclusion with the orbit, with the circular orbit, but if you continued this experiment where you pack more and more explosive into the cannon, then what happens is that the object turns into an elliptical orbit where it no longer revolves around the center of say the Earth. It actually revolves around the center of an ellipse. But if you continue to add more and more powder to this cannon, that ellipse becomes more and more elliptical, more and more squashed. The eccentricity gets larger until you reach a velocity that is known as the escape velocity. You are able to actually leave, the orbit becomes unbound. You are actually able to leave the gravitational influence, as it were, of the Earth. You're able to move out into space and not fall back down towards the Earth's direction. And this is referred to as the escape velocity. For the Earth, that escape velocity is 11.7 kilometers per second, or Mach 24. 24 times the speed of light, or the speed of sound. So the astronauts, or anyone that wants to blast off from the Earth, is going to be traveling at that rate of, needs to obtain that outward velocity of 11.7 kilometers per second. Obviously, for the moon, much easier to get off the moon because, again, the force of gravity is 1/6. So, if you do the math, the escape velocity is much smaller. And the escape velocity is defined as this. So the escape velocity is square root of 2 gm over r. So if you were to relate the escape velocity to the orbital velocity, then the escape velocity is going to be the square root of 2 times larger than the orbital velocity of this in the same circumstance. So say the same circumstance being the Earth or being around the moon. And when we look at we now start to address the astronomical consequences of all this. Kepler, the Copernican model, basically noticed that the speeds of the outer planets decreased as you moved further out. Jupiter does not move in the sky as fast as Mars does. And Kepler took it even further because he had Tycho's observations, and he was able to mathematically derive the harmonic law, his third law of motion, or planetary motion, which stated simplistically that the period of a planetary orbit squared is equal to the size of its orbit cubed. Now, Newton came around, but the problem, or the issue, I suppose, with Kepler's laws, it was that it was a relational law. You needed to basically compare one planet to another. Newton decided, all right, well, one of the things that I need to test is, obviously, I need to see whether or not my law of gravity works for planets. Because what is that force that's keeping the planets in orbit around the sun? Newton correctly deduced that force was gravity. The same force that moves the apple to the ground is the same force that causes planets to orbit around the sun. And so he said, well, if that's the case, then I should be able to reproduce Kepler's law in some form. I should be able to use gravity to get to the same conclusion that Kepler came up with. And he did. So again, through mathematical derivation, which I've done myself, you can derive this law, which is from his laws of motion, which is now that the period squared is equal to the radius cubed. Now it's an absolute value. So if you know the period of one planet and you know its orbital size, then you can compute this. But there's an additional factor where the radius cubed is equal to 4 pi squared over g, the gravitational constant, divided by m. This is really, really useful. So again, because Kepler's law was relational, this whole 4 pi business went away. Basically, it divided out of the equation. But because Newton was able to absolutize, that's a word, absolutize the Newton's law, or Kepler's law, we now know that the mass of the object the masses of the object are relevant. So specifically, this is a simplified version of Newton's laws, but in actuality, that big M is the sum of the mass of the Earth and the mass of the Sun. But because of if you're addressing the solar system, the mass of the Earth in relation to the mass of the Sun is essentially negligible, so the mass of the Earth can be ignored. And so now we have an opportunity to weigh, or mass, the Sun. We know what the gravitational constant is because we can do experiments on the Earth to derive that. The most famous would be backwards engineering the Cavendish experiment. Good. The Cavendish experiment can give you, while it was not originally designed to do this, you can get the gravitational constant from it. 4 pi squared is a mathematical constant. We know what the period of the Earth orbit is. Obviously, it's 265.25 days. And because of the transit of Venus, we know what the radius of the orbit is. We know the distance between the Earth and the Sun. Now, because of Newton's third law, because of Newton's revision of Kepler's third law, we can rewrite that equation seen at the bottom right, and we can get a mass of the Sun, or at least we can get a mass of both the Earth and the Sun. But again, the mass of the Earth is fairly negligible, so bing, bang, boom, mass of the Sun. We can do this, and because, again, it's absolutized, and I'm going to keep that word, it is now a word, we can do this to other objects. So the moon, or Jupiter, for example, if we look at the Galilean moons, if we can say, for example, take the period of Io's rotation or revolution, and we can determine how far away Io is from Jupiter, we can determine the mass of Jupiter, because Io's mass is essentially insignificant to Jupiter's mass. And the really cool part is we got 4 of them. We got Io, Europa, Ganymede, and Callisto. You can do this with all of them, and you can get the same mass. You get about 310 times the mass of the Earth. So, awesome check to Newton's laws. And this applies to anything orbiting around something else due to the presence of gravity. A star orbiting around another star, a galaxy orbiting around another galaxy. So, without this, without Kepler, and without Newton, we would essentially have no way of deriving the mass of astrophysical objects. So, astronomers are very thankful for Kepler and Newton, because that allows us to determine one of the most fundamental properties of astrophysical objects. Because again, mass is, particularly if we want to know how things move, mass is related to force, and in this case, the force is derived from gravity. Now, I'm going to end this lecture by talking about Newton's problem, or qualms with gravity. We now refer to gravity as action at a distance. Essentially, he defined it, or he referred to as action at a distance. That was problematic, because there was no, at the time, there was no other example of this. All other examples of force, you had to make physical contact. There was one, the action was one object smacking into another one, or one object holding on to another one. There was no distance between the two. And so this idea of a force acting upon another object at a distance, without apparent physical contact, troubled him. And so, while Newton believed that his laws were accurate in describing the motions of things, he fundamentally had a problem with not understanding why. What was that physical mechanism? Why did gravity work itself out? And that ties back to Einstein's relativity. Einstein's relativity now gave us an understanding of why. Einstein believes that the reason why things are attracted gravitationally is because of the curvature of reality, or the curvature of space-time. And with that, I bid you all adieu. Peace out, and as I said in Lecture 7, Lecture 8 will be about one of my favorite things, which is exoplanets.